all animals eat. Some would like to eat us.
You need to back up. Yeah.
But why are humans the only animals that cook? I'm David Pogue, and on this episode of Nova Science Now, I'm on a mission to find out why is cooking so important.
So amazing.
You eat every day, but do you have any idea what really goes on inside your oven? How does this disgusting carcass become the most delectable meal of the year?
Mon Dieu! I have discovered browning!
I'll be diving deep inside my dinner.
Most of flavor comes through your nose.
Freaking me out!
And deep inside the mind to unlock the mysteries behind the foods we crave.
The taste system solves problems that if you don't solve them immediately, you die.
Is it possible that cooking, in fact, made us who we are?
Cooking has enabled us to dominate the earth.
From the gorgeous to the grotesque.
Oh no, they're writhing!
No, this is really scientific.
We are getting the answers. How we got them might surprise you.
You see the rat in there? You're doing some kind of brain meld on me.
You definitely look like a super taster.
Hey?
Up next on Nova Science Now, can I eat that?
Funding for Nova Science Now is provided by the National Science Foundation, where discoveries begin, and
discovering new knowledge, biomedical research and science education, Howard Hughes Medical Institute, HHMI,
and the Alfred P. Sloan Foundation, supporting original research and public understanding of science, technology, engineering, and mathematics, and the George D. Smith Fund. And by PBS viewers like you. Thank you.
Thanksgiving, America's favorite holiday meal. A golden brown turkey and rich stuffing. Delicious. But a few hours ago, it wasn't such a pretty picture.
Look at this stuff. This is what we make Thanksgiving out of. They're like roots that make you cry and vegetables that are completely flavorless. This stuff, you could set a home run record with this thing. And we eat dead animals. Where did this idea come from? What could be more appetizing? And yet somehow, through chemistry, through science, this stuff is going to coalesce into this fabulous meal. How the heck does that happen?
To find out, I'm going to a very special laboratory. America's Test Kitchen.
Welcome to the test kitchen. You need to put this on.
This is where the PBS show and the magazine Cooks Illustrated are made. Check out how they test the tenderness of a hamburger.
No, this is really scientific.
So it looks like a 4.5 on the splatter scale.
That's a really tender burger.
The bigger the splat, the better the burger. Unlike most kitchens, they employ an organic chemist to help figure out what is going on.
When you had the skin on and the bone in, you got more variation.
We got a lot of variation.
Guy Crosby teaches nutrition at the Harvard School of Public Health. Here, he uses his science to make recipes better. Today, the goal is a perfect turkey filled with succulent juices. But frequently, that isn't the case. The dreaded dry turkey is a pop culture cliche. And something we're all probably a little too familiar with.
I mean, this is just a waste of a Thanksgiving right there.
So why is that? A raw turkey is made up of about 75% water. It's also not very appetizing, and it's potentially lethal to eat because of the bacteria growing in it. So, of course, you've got to cook it. The problem is that takes hours, and all that heat can evaporate the water right out. So, is there a way to get more moisture into the turkey before cooking it and keep it there?
I like to use the seasoning injector. It's like a prop from Pulp Fiction. I can save him! Right into the heart. Is that a good technique?
I recommend brining in a bucket.
The cooks at America's Test Kitchen have discovered one way. They recommend soaking the whole bird in salt water overnight, a process called brining, which adds moisture to the meat. More moisture will make the meat more tender and juicy. Let's back up and see what is really going on deep inside the turkey. Meat is mostly muscle, made up of millions of fibers that are like electrical cables bundled together. Each fiber is a long cell made up of protein and mostly water. When you heat the meat, the fibers contract and squeeze out that moisture. The more you cook it, the drier the meat becomes.
I thought we were just sticking a bird in some salt water.
Yeah, well, we are, but a lot of chemistry's going on in there.
If you put a turkey into water, the H2O moves into the meat through a process called osmosis. Osmosis creates a natural force that pulls the water across the cell membrane from the higher concentration of water to the lower one, so they're in balance. Now, meat would also absorb plain water, but the salt is key for a juicier turkey.
The salt will help the muscle fibers to expand, create gaps, and that makes room for more water to get in.
A few hours later, I get the tough job of analyzing which turkey is juicier, the brined or the unbrined.
Ladies and gentlemen, sample A. Okay, that needs some serious gravy. And here we go with the second sample. Wow. That does not even need gravy.
So you can see the brining at work.
The brined turkey is moist and juicy, while the unbrined...
This, I would not finish that piece. I mean,
It's really dry. You need
super dry.
half a cup of gravy to choke that down.
Not all chefs and scientists agree that a brined turkey is tastier. For some, it's even too salty.
So we're going to see how tender they are using this instrument called a texture analyzer.
Guy, always the scientist, puts the turkey to the test.
You're gonna put your turkey into a tender testing machine? You must
Absolutely.
be a gas at Thanksgiving.
At Framingham State University, Guy can measure the force it takes to penetrate the meat.
It's really like chewing in slow motion. So we're directly measuring if it takes more force to chew one versus the other.
Side by side, we have a winner.
Whoa!
This is about a 20% difference.
The unbrined breast takes 20% more force. The tenderness machine agrees with me.
The Pogomatic 3000.
Okay, so we solved one problem, making the meat juicy and tender. But what about flavor? The perfect turkey is juicy inside, and outside it's got to be crispy golden brown. That color ain't just for looks. It turns out browning the outside of meat is crucial for creating the most delicious flavor, thanks to a complex chain reaction.
Now, if I'm not mistaken, Mr. Food Chemist, there's some food chemistry going on here.
You're absolutely right.
The key to browning and producing the best flavor is heat, lots of it. The cooks show the difference on chicken cutlets, which are a lot easier to brown in a fry pan than a 20-pound turkey. Heat is a form of energy that is transferred into the food. That energy can speed up the molecules inside the food, causing many possible changes. One of them, that happens quickly once the surface of the meat gets above 300 degrees, is called the Maillard reaction.
The Maillard reaction was discovered by a French chemist in the early 1900s named Louis-Camille Maillard, and
Mon Dieu! I have discovered browning! Henceforth, it shall be named after moi, Maillard.
I'm sorry, I was just thinking of something.
The Maillard reaction happens on the molecular level. As we've already learned, meat is mostly muscle, which is made up of protein. Proteins are made up of molecules called amino acids. the heat from your stove breaks down the bonds in protein chains, releasing the amino acids.
So it's actual chemistry that's being driven by the heat. So if you have something that's not going to heat up, you don't see these reactions taking place.
Next, those amino acids react with sugar that's also in the meat. That sugar was there to provide the turkey's muscle with energy. Now, on the sizzling skin, sugar and amino acids combine to create new molecules that give the turkey that delicious roasted flavor we love, and the brown color.
You take something simple, a few molecules, sugars and amino acids, and together when they react, they can lead to 1,000 different new flavor molecules created by the Maillard reaction.
And Maillard's delectable browning chemistry isn't just for meat. You can thank the same reaction for the irresistible flavor of many things we roast, including coffee beans and chocolate.
Something you see in an automotive factory.
Oh, watch this. It's like Transformers. Gone.
You just don't want to turn it on when it's like that.
No.
Little drinking fountain.
Clean up on aisle 4.
My thirst quenched, we've got to finish off the turkey. And that means it's time for that delicious combination of stale bread, tasteless celery, and tear-worthy onion, the stuffing. First, you have to battle the onion.
You know, the way you prepare onions has a huge impact on the end result. I want you to smell this onion. Can't really smell anything.
It doesn't have any smell.
No.
Have you done something to this onion?
No, that's just a regular onion, but I'm gonna show you something. So if I just take this onion and cut it right in half by taking the blade and slicing, I've started a chemical reaction, and now you can start to smell an aroma.
Yes, I do.
Yeah.
It smells like onions.
Onion.
The more you cut an onion, the more of that chemical reaction happens, and the stronger the taste. Inside the cell of an onion, there are enzymes. These are normally kept separate from the other molecules by a barrier. When your knife cuts the onion, these chemicals come together to form new molecules. Some make you cry. Others create the strong onion flavor.
So you're actually changing the flavor of a vegetable according to the mechanical action of cutting it.
That's right. The more you go at it and the more you release those cell walls, the more flavor and the more pungent aroma is going to come out.
One of the new molecules is propane-thiol S-oxide, a volatile molecule that floats up and can trigger the tears. Assuming you survive onion cutting, it's time to move on to the rest of the stuffing.
Bridget, you appear to be the maker of the croutons. So this is how you make real stuffing?
That's how you make real stuffing.
I thought it comes in a box. No?
Only if you're desperate. The key to great stuffing is getting the moisture out of bread.
Unlike the bird itself, where the big challenge was keeping the water in, stuffing presents the opposite dilemma, getting the water out. If you fail, you get this, mushy, gummy stuffing.
Hate gummy stuffing.
That was one of the Pilgrim's top 10 most hated things.
Most recipes call for using stale bread, but at Cook's, they have discovered a problem with that. In stale bread, the water actually gets trapped inside the crystal structure of the starch granule. So while the bread may feel dry, it actually has lost very little of its water.
So if you were to reheat this, wrap it in foil, you could actually bring back this baguette and be really nice and moist, and you could eat it. But for our stuffing, it's still going to be too moist. That's going to make a stuffing gummy.
So how do you avoid the gummy curse?
So you want to cut the bread into cubes, and then we dry these in a really low oven, about 250 degrees. And that's perfect because it's going to basically dehydrate the bread.
So now, inside the starch granule, there's much less water.
So you can see that it's still moist, but the cubes are not turning to paste.
Thanksgiving saved.
So that's our science lesson in the chemistry that will be happening in your kitchen when you cook your turkey.
That is delicious, Bridget.
From making a tender and golden brown, delicious turkey to yummy, not gummy stuffing. Now that I know a thing or two about how to cook, it makes me wonder, why do we even cook at all? Throughout history, man has sat around a fire cooking and eating. But we humans are the only animals that eat cooked food. Surely there is a good reason for it.
Cooked food gives you enormously more energy, and so for a certain amount of food, you get many more calories.
Richard Wrangham is a primatologist in the Department of Human Evolutionary Biology at Harvard. He thinks that cooking was essential to human evolution. He says cooked food is easier to digest, and so humans evolved to use their food more efficiently. This is the skeleton of an ape, and he's comparing our anatomy with our ape cousins.
The typical ape has got this very broad rib cage going right out there and flaring out, foreshadowing the fact that it's carrying a big gut down here.
And you're not talking about a pot belly. You're talking about...
We're talking about the small intestine, the large intestine, all of the stuff that is actually responsible for the digestion.
So the simple invention of cooking produced these enormous changes in our skeletons.
Yeah, it paid us, once we ate cooked food, to get rid of all of this gut, because that's expensive, so it's efficient to get rid of that.
How can cooking change who we are? Understanding that, and how we get energy out of our food, is what Steven Secor studies.
They have the potential for killing you simply from constriction around the neck.
Great. Secor, a biologist at the University of Alabama, works with a creepy, crawly, dangerous array of animals.
You need to back up.
He's trying to understand how all animals get the energy they need from what they eat. Check out how a python chows down.
Here I am. Here, sneaky, sneaky, sneaky.
In the case of these guys, the food is very raw. These rats come frozen as snake food.
Okay, there we go, there we go. There we go, there we go, there we go.
Whoa! One of Secor's favorite animals to study is the Burmese python.
It's supper time.
It is.
Down the hatch in one big bite. Pythons can eat more than a quarter of their body weight at one sitting.
How is the digestive system different from ours?
Most of their digestion is identical to ours. It's just all very long and slender.
A python is basically one long gut. So to see inside, we take one to a nearby veterinarian's office for an x-ray.
Hey look, snakes welcome.
Good. Yep, yep.
Wow. You see the rat in there.
Oh, it's perfect.
Sure enough, there it is, the python's dinner.
The head of the rat is in the pit of the python's stomach, and the stomach extends back, and from this point on, that's esophagus.
Inside the stomach, acids break down the rat, bones, blood, and all. Secor x-rayed the python over 2 weeks. Bit by bit, the rat disappears, and all but the hair is absorbed by the python. Understanding where the disappearing rat goes can help us understand how our food nourishes us. Minus the bones and fur, of course. To make this point, Secor says it's useful to compare the rat with a cupcake. After all, to a python, a rat is basically a triple-layered German chocolate cake.
Here we have the cupcake and the rat. Both of these have energy stored in them.
Now, even though we don't find these two treats equally appetizing, from the point of view of digestion, what they have in common is that they are both full of potential energy, or calories. To understand what kind of difference cooking can make to your food, you need to first understand a calorie.
Calories represent the amount of fuel that's present within either one of these food items.
Calories are a way of measuring the energy in food, energy your body, or a python, needs to function. Think of this cupcake as fuel, like a log on a fire. If we burn it, that fuel will increase the heat of the fire. A calorie is a way to represent that increase.
Let's burn the cupcake.
Okay.
So it's actually burning like a
Yes.
charcoal briquette or something?
Yeah, so like a log.
Burning the cupcake like this, in the open air, it's impossible to measure the heat it gives off. So Secor shows me the right way to do it, using a machine called a bomb calorimeter. Items put in the bomb calorimeter must first be dehydrated, since water doesn't burn. Luckily, Secor is prepared for that.
This is a dried rat that has been ground up. All the water out of it, kind of mixed it all up, and then formed a pellet.
All right, we'll bring on the bomb calorimeter. A portion of the dried rat goes into the bomb calorimeter, where it's burned in a special tank sensitive enough to measure the heat or calories in the rat. We do the same thing with our pink cupcake. Dehydrate it, grind it up, make a pellet, and, as the grad students like to say, bomb it. Okay, Professor, a nation of eaters awaits the results. The bomb calorimeter says that 7 ounces of cupcake has twice as many calories as 7 ounces of rat. Impressive and disgusting. Now let's take it one step further. Those calories come from the basic elements of eating: proteins, carbohydrates, which are simple sugars, and fats. Secor has calculated the percentage of each in our cupcake and rat. No matter what we eat, whether it be a cupcake or a rat, those are the things your body's going to extract.
That's right. And how they differ and how all meals differ is the relative proportion of each of these elements.
What's amazing is the quantity of sugar in this thing. I mean, it's almost the entire cupcake by volume, and you know, the fat is quite a dollop too. And over here we have so much protein and far less sugar and fat. The rat looks like it'd be a healthier lunch than the cupcake.
Right.
Fat, sugar, and protein give me the energy to fuel my activity. And Secor can see how much I need by measuring my oxygen use. It turns out that the act of digesting a meal takes energy too, like that big plate of barbecued ribs. Even as I lie here, my body is working to break down that dinner. And that energy I burn digesting takes away from all the fuel in the food. Some of the calories are always lost in the process. And that is where cooking comes in. Cooking made digesting easier.
When food is cooked, our body doesn't have to work as hard to digest it.
Wrangham says that cooked food gave humans extra energy compared to their primate relatives.
And where are we putting it? Here is one big place. This brain is about 3 to 4 times the size of this brain.
The human brain requires approximately half a cup of sugars a day to function. That's a lot of calories. So it was our brain, the largest proportionally of any primate, that Wrangham believes benefited most from a nice cooked meal. It seems we humans have always figured out clever ways to fill up with less effort.
Hi, could I have the #1 burger, no skin, bones, or feathers, please?
No, not that way.
Thanks a lot.
But with tools like spears or knives, as well as cooking. Wrangham says getting more energy out of food with less sweat was a key factor in human evolution. Cooking was a real time saver.
It takes a lot of time to chew. So if we were a great ape, like a chimpanzee or a gorilla, we estimate that we would have spent about 6 hours a day just chewing.
What?
Yeah.
Wow, their floss budget must have been immense.
Humans are completely off the curve.
Now, there's one problem with Wrangham's theory. There's no evidence they built fireplaces suitable for cooking until around 400,000 years ago. And we know that the human brain was already evolving long before that, about 1.8 million years ago. Wrangham is confident that older evidence of cooking fires will eventually turn up. But in the meantime, he's hunting for other evidence to support the theory. When he heard about Steven Secor's work, he wondered if the snakes could help to illuminate just how much energy cooking actually saves. Secor can easily measure the energy it takes a python to digest food, just like he was able to measure how many calories it took for me to digest that plate of ribs. But there was a problem. Pythons don't eat what we do. They like their meals furry. So how do you make a python eat a steak? That was a challenge for Secor and his grad students. Believe it or not, this is what they figured out. They sewed a rat's face onto a steak.
You have little meat stick rat puppets.
That's right.
Why not just take a cooked rat?
We wanted to use a food that was similar to what we might be eating. So we need to sort of entice them to eat the steak.
Clearly, science takes ingenuity.
You could tape the face of a cupcake onto a big piece of broccoli and feed it to children.
Success! Once full on that rat-faced steak, Secor put his python into this Tupperware, a makeshift oxygen tank, so that he can measure exactly how much oxygen the snake consumes while it's digesting.
Kind of like when I was on the treadmill with this thingy.
Pretty much the same principle.
But they don't make treadmills for snakes, so...
And with that, he can figure out the caloric cost of digesting the raw versus cooked meat. The result? It turns out that cooked steak takes 12% less energy for the python to digest than raw steak. Say what you will, the rat-faced meat experiment worked. So what about vegetables? Not even a rat's face will make a python eat broccoli. Fortunately, bearded dragons love vegetables, raw or cooked. The bearded dragon experiments show that cooked vegetables take 40% less energy for them to consume than raw ones. So the python and the bearded dragon help to show that eating cooked food takes less work to get the energy from the fat, protein, and sugar in our food. There's still the unsolved mystery of when campfires and cooking started. But we know that the impact of cooking has been enormous. Brangham says cooking changed many things for humans by giving us more time and energy to communicate around a fire, or even more time to make babies.
So cooking really has, astonishingly diverse impacts on our lives.
Cooking? A little thing like cooking has produced these enormous spatial changes?
Cooking seems like a little thing until you go without it. I think of this as the most significant increase in the quality of food in the history of mammals and maybe in the history of life. I mean, this was enormous. It has enabled us to dominate the earth.
And it's delicious, too. For me, the most important thing about food is, of course, the way it tastes. But how come different things taste good to different people? Like some people go nuts for French fries, while others salivate over salad. I want to know what's going on. So I've come to San Francisco on a mission, and it's not just to eat at great restaurants.
Hi. Hi. I'm David.
Monica Martinez is cooking up something new that has me freaked out.
This is my kitchen.
The central ingredients have just arrived from FedEx.
Please don't tell me these are air holes.
Yes.
They're alive?
They are alive.
Oh, God. Oh, no. They're writhing.
And it's not just wax moth larvae. In box number 2...
This has to be done fast, because they jump out.
Crickets?
I have no words.
Monica is drawing on her Mexican heritage to develop a signature snack and prepping for tonight's foodie event called Off the Grid.
When I cook them, I just pan fry them.
The recipe is simple. Take 2 homemade tostadas, add avocado and zucchini, and then, for the bit that makes my taste buds tremble, a generous sprinkling of crickets.
Here's to all our 6-legged friends.
It tastes amazing. Crickets have their own flavor, so they taste really good.
It's not the food, it's the concept. It's the thought of what I just saw come out of that hideous FedEx box.
Yeah.
But if you hadn't told me, I'd say these are some of the best tacos I've ever had.
Eating bugs reveals there's more to taste than just taste buds. So what really does go on?
Would you mind taping your nose?
Excuse me?
Just close it like this. I'll do it with you. Just gonna take one of your nostrils and kind of plug it, and then plug the other one.
Oh my gosh.
Barb Stuckey is a professional taster for a food product company called Matson near San Francisco.
So now go ahead and put some and swish it around your mouth.
Okay. Water.
Take another swish, and this time when you're swishing, let's take the tape off.
Okay. Oh. Oh my gosh! It turned into brown butter.
Most of flavor comes through your nose.
Freaking me out! Wait a minute, but it was inside my mouth. I couldn't have smelled it.
Oh, yes, I could. Inside our mouths, there's a back channel to our smell receptors. Volatile molecules, or vapors, rise off food in our mouths and trigger our sense of smell. But if your nose is blocked, the vapors aren't pulled up into the nasal cavity and you don't smell them. It turns out our nose plays a big role in the creation of flavor, the total experience of food.
It feels like the flavor is coming from your mouth, but in fact, it's coming from your mouth through your nose, and the aromas are detected in your nose.
And smell isn't our only sense at work. Barb asks me to try a new juice they've just created.
It's definitely not fresh squeezed.
What would you say if I told you that was apple juice?
Wait a minute. You're doing some kind of brain meld on me.
Yes, but
this is clearly orange juice, but it tastes like apple juice. So what have you done here?
All we've done is taken apple juice and added a little bit of orange color.
You're kidding.
So it looks like orange juice.
Gosh, I'm such a sucker. I can't believe I fell for that. It's perfectly good apple juice.
It's very good apple juice, yeah.
Barb says not only smell and vision, but even sound can influence taste. So I'm blindfolded to see if cold water sounds different from hot water.
Wait a minute! I could tell that the second one was hot. How could I tell that the second one was hot?
All right, take your blindfold off. The second one was hot.
I know, I could hear that it was hot, but that makes no sense. It had a hot water sound.
Believe it or not, hot water has a different pitch when it hits the cup than cold water does.
Everyone gets it right. Sound gives us information about not just temperature, but freshness, crispiness, crunchiness, texture, fat content.
You don't actually put thought into the sound these foods are gonna make, do you?
Of course, very much so.
Here at Matson, they're trying to make treats so delicious that you will crave them and buy them.
And honey, there's no fat. Or no sugar.
To do so, they use their understanding of how flavor works and food science to engineer flavors that appeal to all your senses.
Flavor, that concept, comes through many different senses. Really, when you're experiencing food and you say you like the taste of something, you really like the way it looks, the way it feels, the way it sounds, the way it smells, and the way it tastes.
You have a gorgeous tongue.
Thank you.
To get a better understanding of the difference between taste and flavor, I'm having my tongue examined by the guru of taste, Linda Bartoshuk of the University of Florida.
You never see taste buds. They're not visible on the tongue. Taste buds are buried in the tissue of this little mushroom-like structure, fungiform papilla.
Do I have that?
Yes.
Is there a cure for it?
You don't want a cure for it.
Okay.
Those things are really good.
The surface of your tongue is covered with mushroom-shaped structures called fungiform papilla, which house the taste buds. Bartoshuk uses a card with a hole about the size of a pea and then counts the number of spots on my tongue. Her blue dye reveals the fungiform papilla.
Ooh, wow.
Some people taste things more strongly for the simple reason that they have more taste buds. Bartoshuk calls them super tasters.
Wow. You're up between 50 and 60 fungiform papilla. This is very, very high.
Really?
From what I can see now, you definitely look like a super taster. So that's pretty well-endowed tongue.
Sweet. Literally. To see how it works, let's zoom into a taste bud where there is a sweet receptor. If we drink some of that orange apple juice, the sugar molecules in it bind with a sweet receptor. That then sets off a series of chain reactions that sends a signal to the brain that you are eating something sweet.
When you eat a piece of candy, you're experiencing more sweet than I am. And you have not only more taste buds, but you, in addition, have more pain fibers because every taste bud is surrounded by a basket of pain fibers. So if you eat jalapeno peppers, they're going to be at least twice, perhaps 3 times as intense burning as I would get.
That explains so much. I can't tell you the number of dinners I've had where everyone's like, oh, you're such a hot pepper wuss, Pogue.
Yeah.
It's not that. It's just that I'm suffering 4 times more.
Yes, yes, you're experiencing considerably more burn.
I think I got it all.
Certain tastes are hardwired in your biology. These basic tastes are the ones that trigger receptors that you have on your tongue. Sweet, sour, bitter, and salty. Some also think that the savory flavor of meat or cheese is a 5th basic taste called umami.
The brain is built to make sure you experience those tastes. It's wired that way. And the reason you're wired to like sweet is so that a newborn baby will nurse immediately without having to learn because mother's milk is sweet. At the same time, the reason you want to build in a dislike for bitter is so that if you put anything in the child's mouth that's toxic, and most toxins are bitter, the child will spit it out and make a fuss.
Bartoshuk says these basic tastes were key in our evolution.
The taste system evolved as the true nutritional sense. It solves problems that if you don't solve them immediately, you die.
As basic as flavor is, there's an awful lot we don't fully understand about how it works. And at research centers and universities, there are a lot of people working to figure it out. Gordon Shepherd of Yale University is mapping how our brain gets involved in processing flavor.
Flavor is not in the food that we eat. Flavor is not in the molecules. The perception of flavor is created by the pathways in the brain.
Thankfully, instead of dissecting my brain to prove his point, Shepherd kindly uses colored tape.
This is representing the pathway of smell. Next comes taste.
Each different color represents the pathway inside the brain that information from our different senses travels, like the signal from the taste buds.
So here we go with sight, hearing, touch.
These pathways run throughout the brain.
It's mind-blowing. You're saying that the simple act of eating, the simple pleasure of eating something involves circuits all over my brain, zipping everywhere at once.
The way that the brain creates flavor engages more of the brain than almost any other behavior that we take part in.
As we try to understand the power of the brain in creating flavors and creating our cravings for those flavors, the science of taste is moving into new frontiers.
The problem is our evolutionary mechanisms did a great job to make us survive, but evolution didn't know we were going to live so long eventually.
Our system of taste evolved for a world where food was scarce and starvation was a real threat. In today's world, the bigger problem is coping with the abundance of food. one where our evolutionary craving for fats and sugars can be a liability. Even so, delicious foods are one of life's great pleasures. Even foods we never thought would be delicious.
Monica, I can't believe you have a line here.
I don't believe that.
Maybe I was giving the bug short shrift. Maybe there's something to this.
New research shows that the more choice we have, the more likely we are to overeat, like gorging at a buffet, or here at the San Francisco foodie event Off the Grid, because variety sparks our interest.
One bacon and egg popsicle.
It's like what Gordon Shepherd said as he was putting colored tape on my head. Experiencing flavor probably engages more of our brain than almost any other activity we do.
Wow, so amazing.
Shepherd believes that would include exercise, work, or even sex.
Basically, I think what it boils down to is superior lubricity and retronasal olfaction.
Think of that next time you take a bite. Meet Nathan Myhrvold. He makes his living as a technology business mogul, but this is where he comes to indulge his real passion.
I've been interested in food my whole life. Very enthusiastic eater and interested in all aspects of creating it.
And now he wants to revolutionize the way we cook by bringing cutting-edge science into the kitchen.
We aren't just trying to do our grandma's recipes. We're trying to focus on understanding the scientific basis for what is this thing we call cooking.
Nathan is making wild new concoctions, like cotton candy that tastes like grilled cheese, or butter made not from cream, but from peas, and short ribs that he cooks in warm water for 3 days.
Some people call him Willy Wonka, some people call him Mad Scientist.
Please welcome Nathan Myhrvold.
And his Wonka-esque flair has made Nathan a regular on the talk show circuit.
We've been cooking this pastrami for 72 hours just for you.
Am I going to die from eating this meat?
Why don't we find out?
Let's find out.
I got into this by trying to understand it myself.
So he's become a gourmet evangelist, writing his own cookbook, one that's really, really big. 43 pounds of science that's so heavy it comes with its own plexiglass bookcase.
Was the idea to publish something that you couldn't possibly shoplift?
That was it.
Its 2,400 pages lay bare just about every aspect of cooking, like what makes meat tough or tender? How does a microwave work? And what's the best way to cook broccoli? It's all the culmination of Nathan's lifelong love affair with food.
When I was about 9 years old, I announced to my mother that I was going to cook Thanksgiving dinner. And I went to the library, got this whole pile of books. I'd love to say it all turned out great. It didn't. But sort of from that point on, whenever there was serious cooking at home, I was the one who did it.
But Nathan soon fell under the spell of another passion.
I remember once I saw an episode of Doctor Who, the British science fiction series. The Doctor is being asked by this guy, what are you?
Are you some kind of scientist?
I'm every kind of scientist.
I thought that was so cool. So I wanted to be every kind of scientist.
So Nathan went on to earn degrees in economics, math, and physics.
Ultimately, my PhD is in mathematical physics, focusing on quantum field theory and curved spacetime. And I worked with Stephen Hawking.
And Nathan taught himself about even more topics by obsessively reading about them, every book he could find.
For a while, he was Amazon's #1 individual customer.
Since the 80s, he has been at Microsoft, where he is in the advanced technology group. What we're talking about is all the world's computers connecting to each other.
It's all the world's people connected to each other, with computers simply as the means.
Nathan was a visionary in the hottest field of the day, computers. But he never forgot about his first love, food. He still wanted to understand the science of cooking.
I thought, well, there must be some big textbook that says all this. Not only was there no single book, there was no stack of books.
Nathan decided he would find answers on his own. He would use science to push the boundaries of cooking in the form of a book.
I'm writing the cookbook that I wished I could have just bought.
Nathan started by hiring a team of experts and turning a warehouse into a Wonka-esque playground.
It's one of the best equipped kitchens in the world. We've got a rotary evaporator, freeze dryer, combi oven. We've got an industrial jewelry bath that we use to make our ultimate French fries.
A whole variety of homogenizers.
Blowtorches, liquid nitrogen.
A centrifuge is fantastic. Normally, you'd never get this special layer that we call pea butter. Oh my God, does it taste good.
Nathan wanted to figure out exactly what's happening from a scientific perspective when we put flame to food.
Our goal was to show people a vision of food they hadn't seen before. So I had this idea of let's cut all these things in half and show a picture of the food in the pan, in the oven.
So they revved up their table saws and began hacking open every appliance they could find. And every type of meat.
We want both the whole stick of muscle.
This junkyard of cracked open grills, microwaves, and gas ranges gave Nathan new tools to show how heat moves through food and irreversibly changes it.
They're all things that happen so fast that when you look at it, it's like, oh, well, it happened. If you slow it down, you see how and why it happens.
One recipe Nathan was determined to dissect: how to cook the perfect steak.
Here we're looking at what happens when you sear meat. See what the structure is inside that crust.
Nathan became obsessed with the Maillard reaction. That's the one I learned about in the test kitchen, in which high heat releases amino acids and creates delicious flavors. Meanwhile, inside the steak, other forces are at work.
The physics of water is central to cooking because food is mostly water. All steak that you cook is actually boiled on the inside.
The problem is that the boiling interior cooks more slowly than the edge of the steak near the flame. So chefs have to make a choice. Do you undercook the inside or overcook the outside? Nathan searched for a way to have it all. And he heard about chefs who were experimenting with a technique that was first used in the most unlikely of places: hospital kitchens.
So they invented this technique in France, where it's called sous vide, where you vacuum seal food into a plastic bag, and then you cook it inside that plastic bag.
And here's how it works.
This is a chamber vacuum machine, and then when I close this, it's going to start pumping the air out.
Nathan then drops the sealed meat in a computer-controlled bath, which will heat the whole steak to the exact temperature of the water. So you can make the entire cut of meat 130 degrees Fahrenheit for medium rare, no part over or undercooked.
Sous vide cooking recognizes that when you have two goals, perfect doneness on the inside and a nice crust on the outside, that you should treat those two goals with two different cooking methods.
When the meat reaches the exact temperature Nathan wants, it's Maillard time. Nathan's weapon of choice, a blowtorch, or a new technique, cryo-frying.
Cryo-frying means that we make something very cold and then we fry it. We want to protect the interior of the food from overcooking as we fry. And you're left with beautifully brown, crispy exterior and perfect interior.
Nathan had cracked the code for the recipe for a perfect steak. And sous vide wasn't the only page that Nathan lifted from the industrial cookbook. He went back to the supermarket to pursue the aisles of ice cream and chocolate sauce. He wasn't looking for a guilty pleasure. He was joining other avant-garde chefs who were questioning the widespread fear of chemical ingredients.
Lots of folks think of this as, oh my God, there's chemicals in my food. Well, I'm here to tell you, food is made of chemicals. Those chemicals are made of elements. And that's the way it is here on planet Earth. Everything actually is a chemical.
Nathan uses chemicals the way a composer uses notes. It's about building something. Just because an ingredient has a lot of syllables or your grandmother didn't cook with it, that doesn't make it bad.
Nathan studied how these chemicals could give him even more control in the kitchen, like how you can use agar to create hot fruit gels, or how xanthan gum can thicken your sauce. And it all went into the book. This culinary Bible grew into the encyclopedic Modernist Cuisine, which requires 4 pounds of ink to print. Determined to spread his message as widely as possible, Nathan soon wrote a follow-up book.
We then decided, hey, let's make one that's for the home. We call it Modernist Cuisine at Home. And that book has got a whole new set of recipes that are all designed that anybody can do them at home.
These science-based recipes don't require an industrial-strength kitchen. Rather, they tell you how to make the perfect mac and cheese by using a pinch of sodium citrate, or how to sous vide a steak using a cooler of lukewarm water and a really hot grill. But the question remains, can all this science actually create food that tastes good?
It's cold.
Nathan shared his cryo-fried hamburger with Jimmy Kimmel, his 72-hour short-rib pastrami with Stephen Colbert.
Oh my God.
And salmon cooked in a Ziploc bag with Martha Stewart.
Oh my gosh. This is a new beginning of science and technology and creativity all mixed together to really create great flavors.
We're trying to show people what's possible. If you understand how cooking works and you understand these great techniques, you have a much wider range of possibilities.
So remember, the next time you take a bite of something, the taste isn't just in here. It's in here, and most of all, up here. And now, we'd like to hear from you.
Follow us on Facebook and Twitter, or log on to our website and tell us what you think. You can see any of these stories again, watch exclusive short videos, and check out our web-only series, The Secret Life of Scientists and Engineers.
You can find it all at pbs.org/Nova Science Now. That's our show. See you next time.
Funding for Nova Science Now is provided by the National Science Foundation, where discoveries begin. And
discovering new knowledge. Biomedical research and science education. Howard Hughes Medical Institute. HHMI.
And the Alfred P. Sloan Foundation, supporting original research and public understanding of science, technology, engineering, and mathematics. And the George D. Smith Fund. And by PBS viewers like you. Thank you. This Nova Science Now program is available on DVD. To order, visit shoppbs.org or call 1-800-PLAY-PBS. Nova is also available for download on iTunes.
A goat and a horse are inseparable for 16 years. A dog befriends a wild deer.
When they greet each other, I've never seen anything like it.
It's time to challenge the notion that only humans form lasting friendships.